Hello, everybody, and welcome to our first lesson that's going to be talking about calculus. We're doing in this order just because the book follows this order. This is actually topic 5 in the syllabus, but there's no reason you have to follow the syllabus exactly. The first part of calculus, there are two parts. The first part is called differentiation, and we're going to start out by looking at rates of change. You should be a little bit familiar with rates of change already, but we're going to look at it in depth because that is the foundation of calculus, is a rate of change. So the first thing we're going to consider is just filling up a cylinder with water, right? So imagine this cylinder started out empty, and we're drawing a graph for time versus depth. So because this cylinder has a constant radius and it's going to fill up at a constant rate, right? As you put it in this water, the depth is just going to increase at a linear rate, right? It's like this graph would be linear because the volume, you could think about each cross section, the volume is the same at the area of each cross section is the same, meaning it's going to just continue at a constant rate. However, if you had a cup like this, then you can imagine when you first started pouring in water, the height's going to increase pretty fast because there's not a lot of area or volume down here. And then as you go up, the rate of the height increase is going to slow down because it's getting bigger, so it takes more water to make the height go higher, right? In the beginning, just a little bit of water makes the height go higher, and as you get up here, more water is needed to make the height go higher, so it takes a longer time for that height to increase. So you can see we start out with the depth increasing fast, right? There's a steep slope, and then that height, the depth, is going to slow down, right? It's gonna, like that, the slope of this thing is gonna get closer and closer to zero because it takes longer, right? It takes more time to have the same change in depth. So this is something you just want to be framing your thoughts with, of like what would these graphs look like, right? If you had to graph time versus depth, what would these graphs look like, right? So I want you to actually try these and see if you can get them. All right, so take a second to actually do it before you watch this video, right? So the first one would be, there's a big area, big volume thing down here. So the height is going to be slow but linear because it's constant cross sections, right? It's not changing as you go up. And then once you hit this cylinder, it's going to then be much faster. The height's going to change much faster. So you might have something that looks kind of like that, right? Slow at first, then faster. This one is going to be slow at first and then gradually become faster. So maybe something like this. Because, at first it takes a long time for the height to change because you have to add a lot of water, and as you go up, it's faster. The height will change faster because you're adding less water. This next piece, for the first piece, is very similar to the first piece of number 1, right? You just have like a pretty gradual straight line like that. And then for the cone piece, it's going to gradually get faster. And then for that little piece, it's going to be straight, right? So you have your 3 pieces, the cylinder at the bottom, the truncated cone in the middle, and then the cylinder at the top. Right, and this truncated cone piece here is curved, and these 2 pieces are straight, right? And then, I know that doesn't look perfect, but it'd be something like that. This one you'd start out fast, right? Because there's a little bit, like the cross-sectional area is small, and then you'd get kind of slow because it gets real big, and then you would gradually start going fast again, right? So you might have a curve that looks something like this for that height. And for the last one, like imagine if you're putting water here, that height's going to change really fast. If you're up here, the height's going to change a little bit slower because you have more cross-sectional area, more volume to fill. So you might start like really fast, and then it's going to kind of get slower, and then it's going to get fast again because that cross-sectional area is getting small. And then that last piece should be, linear. This section here should just be a straight line. So you have this like curvy section, something like that, and then straight line. So we're thinking about like rates of change, right? Like how is the whole time here we've been talking about the rate of change of the depth. And the way we did that is we did depth over time, right? How is the depth changing as time changes, right? So that is what a rate is. It's a comparison between 2 quantities with different units. In this case, depth is measured in millimeters and time is measured in maybe seconds. Right, so we're doing millimeters per second, and that's a rate, right? Some other examples of rates are batting average. If you ever follow baseball, You could say 99.4 runs per inning, right? You see the two different units, and you also see they're being divided, right? So rates are things that are being compared by writing a ratio. Michael Jordan's basketball scoring rate was 30 points per game, right? Meaning, and what you want to think about is this is an average, right? This is all these things we're talking about are average rates of change, right? He didn't always score 30 points. Sometimes he scored more, sometimes he scored less, but if his average rate was 30. And then you can also talk about words per minute as a rate, right? So here's a quick example that you should think about. This Joseph problem. So I want you to take a minute and compare their typing rates. Right, we might want to see like who's a better typer, Joseph or Mary, right? So we could say, okay, Joseph, he can type 213 words in 3 minutes, right? Which is how many words per minute, right? That's what we call a unit rate, is how many words per minute is that. But then he also made 6 errors, right? So he's making 6 errors in 3 minutes, which means he's making 2 errors per minute, and that's a rate, errors per minute, right? Whereas Mary typed 260 words in 4 minutes, but her error rate was 7 errors per 4 minutes, right? And then you could get these unit rates, which let me just get those real quick. Okay, so you can see Joseph, you get that unit rate is 71 words per minute and 2 errors per minute. Marie is 65 words per minute with 1.7 errors per minute. So who's a better typer? Well, this guy is faster but has more errors. She's a little bit slower but has fewer errors, right? And so you could actually, I don't know if you subtract the 2 minus that, you get 69 accurate words per minute. Here you get, 63.25 accurate words per minute. And so I think Joseph's still a better typer. He's not making that many more words per minute, but you can see these are what we call rates, right? And also think these are always average rates, right? Because it takes much less time to write the word a than it does to write the word maybe word, right? Like this one might take you a fraction of a second. This one might take you slightly longer. Or if you had really big words, it would take you longer to write those words, right? So when we're talking about words per minute, this is an average rate, right? He's not always typing at 71 words per minute, or you could even figure this per second, right? So an example of this is, let's pretend you walk 5 kilometers in 40 minutes, right? So we can actually just draw a graph of this. So here's our minutes, and let's say this is 40 minutes, and let's say this is 5 kilometers, right? So let's say you start at 0, 0, which means in 0 minutes you walk 0 kilometers, right? And then 40 minutes later you have walked 5 kilometers, right? And we all hopefully know that distance equals rate times time, right? This is that's like kind of a basic physics thing. Like how far you go is equal to how the rate at which you go times how long you go. And so this person walked 5 kilometers in 40 minutes. In this case, the distance is 5. The rate is what we want to know, and this is 40, right? So the rate would be 5 over 40. Right? 5 kilometers in 40 minutes, or 1 kilometer in 8 minutes. So you're saying 1 kilometer per 8 minutes, or that would be 0.125 kilometers per minute, right? So that's your unit rate. And what this is saying, what you're assuming here, is that basically that 1.125 kilometers per minute is you're just walking at a very constant rate, right? That's the assumption you're making, is you're walking at 0.0125 kilometers every minute, right? So if I just went out 1 minute, we would assume that every minute I've gone 0.125. But do you think that's the case? Do you think people walk at a completely constant rate? Well, probably not, right? Because you probably, maybe you start out walking really fast, and then you kind of get tired, so you kind of slow down, maybe even take a break, right? And then you realize, hey, I'm trying to get exercise here. Let me go faster. So you go real fast and you get there. So really your journey might look more like this. But if you average it out, you end up with this average rate, right? Even though in real life, it's never like perfectly constant like that. Okay, so what we have to think about is when we're doing this kind of thing here, this is finding an average. It's not telling me at every moment, right? So like, let's pretend, how fast, you might ask the question, well, how fast was I walking at t equals 20, right? Like right here, how fast was I walking? Well, you know, if you assume it's average, then you're saying, well, you were walking 0.125 kilometers per minute. But just based on this information, you can't really answer that question because you don't know. Were you stopped at that point, right? Were you taking a break? Or was it during one of the times when you were walking really fast, right? So it doesn't, like, these kind of things don't allow us to answer the question of like, how fast was I going at a specific time? It only lets us answer the question of how fast I was going over an interval of time. And that's exactly what calculus is going to help us do, is calculus can help us answer the question of like, how fast was I walking at any moment in time, right? At an instantaneous moment in time, how fast was I walking? All right, so a couple of things about rate of change. Constant rate of change, you're probably already familiar with, gives us lines, right? If I'm always increasing by 15 when x increases by 1, that's a constant rate of change. No matter where you find your slope, right? Rate of change, as you maybe recognize, is slope, right? Change in y over change in x. No matter where I do this, I will always get the same number, right? Is when I simplify this fraction, I always get the same number. So that's when we have constant rate of change, you get a line, a straight line, and the gradient or the slope on this line is always the same. However, in most real life situations, we don't have a straight line, right? So you might ask like, well, what's the rate of change? What's the rate of change between the temperature at 0 minutes and the temperature at 2 minutes? And so basically you're looking for this slope, right? The change in y over the change in x. And so think about, how would I get that, right? What is this change in y and what is this change in x? So let's define that, right? Remember, slope was change in y over change in x, which in this case, the change in y is 20 minus 5, right? You went from 5 to 20. And the change in x is 2 minus 0. You went from 0 to 2. And that gives you 15 over 2, which is 7.5 degrees Celsius per minute, right? Because the change in y is in degrees Celsius and the change in x is in minutes. And so you get the 7.5 degrees per minute. But again, that's an average slope, right? It's an average slope. What we actually just found was the slope of this line that goes like this. So we found that the slope of this line right here that goes through these 2 points, a straight line. And you can see that that straight line does not perfectly show how it was changing in between 0 and 2, but it gives us an average rate, right? That's what we found, that slope of that line. This line is called a secant line, right? So secant line, and the slope of the secant line tells us the average rate of change. And so I want you to think about, well, how did I find this, right? How did I find the average rate of change? Well, I took the y coordinate minus the y coordinate and the x coordinate minus the x coordinate, right? So I did y2 minus y1 over x2 minus x1, which is, you know, just the slope of a line. Another way of writing this is if we had a function, right? If we called this function f of x, then it would be basically f of x2 minus f of x1 over x2 minus x1, right? So that would be, if we're saying this function is f of x, then this is x1, f of x1, this is x2, f of x2, right? And so it's basically the same thing. It's just a different, function notation for it. So that's how we find average rate of change, right? As we find the slope of the secant line, and secant line is a line that passes through 2 points. There's also something called a tangent line. A tangent line would be the line that passes through exactly 1 point. And that's our eventual goal, is like figuring out how could I figure out the slope of this line that passes through just 1 point? Because the slope of that would tell me how fast I was going at exactly 5 minutes. And so that's our eventual goal, is figure out what's the slope of a tangent line which passes through 1 point. All right, so let's try some practice problems. Okay, so let's look at some examples. The first one, our homework today is going to be on delta math. So I'm going to do some delta math problems. And I find it helpful to put some context in this just for you so you can see. So let's pretend that this is time in seconds and that this is like the depth of water, right? So then we want to find the average rate of change from 3 to 4, right? So we're trying to find the average rate of change between these 2 points. And again, the average rate of change is basically just the slope formula, or if you prefer, or you have to know this, right? It's the function value. So basically, in this case, it would be f of 4 minus f of 3 over 4 minus 3. F of 4 is 9, f of 3 is 3, and 4 minus 3 is 1, and so we get 6 over 1. Think about the units on this, right? These units were depth, let's say in centimeters, so this would be centimeters per second. And so when you get this 6, you're talking about centimeters per second, right? So this might be, the rate of change, the average rate of change is 6 centimeters per second between 3 and 4. Notice how if you find the rate of change between 4 and 5, it would be different, right? So this is not a constant rate of change problem, right? You have something that looks like this, and what we did is we just found the rate of change from like in between 2 points, whereas if I found it between other 2 points, I'd probably get a bigger number, right? So that's how you do a problem like that. Let me get another example. Okay, another one would be you're actually given a function. We want to determine the average rate of change of the function between 1 and 5. So again, let's pretend like this tells me the height of a person in, I don't know, meters, and then x is the time in seconds, right? Just to give us some units so we can start thinking about it, right? You know that, parabolas or quadratic functions have, create parabolas, maybe it looks something like this. If we're going from 1 to 5, we're finding the slope of this secant line telling us the average rate of change between these 2 points, right? And so again, the average rate of change is equal to f of x2 minus f of x1 over x2 minus x1. In this case, it's f of 5 minus f of 1 over 5 minus 1. Right, and again, the units for this, if I was talking about this, so this would be meters and this would be seconds. And so we're going to get something called meters per second, which is going to tell us, the rate of change of this person. In order to figure out f of 5, I need to plug in 5 up here, right? So I plug in 5. That's going to be negative 25 plus 25, which is 0, plus 11. So we're getting 11 here. Minus f of 1 would be plugging in 1 here. I get negative 1 plus 5 is 4, plus 11 is 4 plus 11 is 15, and then 5 minus 1 is 4, and so I get negative 4 over 4, which equals negative 1, and again, if I had the units, it'd be negative 1 meters per second, right? So obviously that's not quite how this one worked. It looks like it was going down, something like this, right? Again, average rate of change. And it would change, right? If you changed these numbers, you would get a different value for the average rate of change because you'd be at a different point on this curve. Okay, in this type of problem, you're going to be asked to plot a segment connecting the points from x equals negative 3 to x equals 3, and then use the segment to determine the average rate of change of the function from negative 3 to 3, right? So because it says x from negative 3, I need to choose this x value here because that's the value of the function negative 3, and then I need to go to 3, which is this one here, right? This line represents the average rate of change between negative 3 and 3. And the slope of this line will tell me the slope of this line is the average rate of change. So I need to figure out what is the slope of this line. Well, one way to do this is to look at the rise over the run. So let me take this guy real quick so I can draw on it. So we're basically just trying to figure out what's the rise and what's the run, right? Because we're trying to find the slope of this line. Well, we went up from negative 70 to 20, so that's a change in 90. And we went over from negative 3 to 3, that's a change in 6. Another way I could have found that is I could have done 20 minus negative 70 over 3 minus negative 3, right? And that would give me 90 over 6, right? So our rate of change is 90 over 6, which simplified would give us, let's see, divide by 3 and you get 30 over 2, so you get 15. So the rate of change, the slope of this line is 15, right? Which means if I go over 1, I go up 15, right? So that right there is a change in 15. That's every step you should go up by 15, which it looks like that's about right. All right, next one. Okay, these are interesting problems. The next one's because they're giving you 3 functions. One is a graph, one is a table, and one is a actual written out algebraic function. And they're asking us to figure out which of them, with average rate of change from 3 to 9, which one has the greatest average rate of change, right? So for example, we'd go, for this one, we'd look for the average rate of change from 3 to 9 would be the slope of this line that goes across like this. Let me go ahead and get it. From 3 to 9, so here's 3, go away, 3, come on now. And there's 9, so we're finding the slope of this line, which again, you can just do y2 minus y1. We're changing from 30 to 60, so the change in y is 30, 60 minus 30, and the change in x, we went from 3 to 9. So we're gonna have 30 over 6, which is 5, right? So the rate of change of f of x is 5, the average rate of change. And if we look at the average rate of change for this one, from 3 to 9, the y value changes from 5 to 53. So 53 minus 5 is 47 over 6. So for the other one is 47 over 6, which this is obviously going to be greater than 5, right? Even without doing that math. And then the last one is you would have to plug in 9 and 3 to figure out those values. Let me take this guy and put him over here. So this is g of x, right? This one was g, is 47 over 6 average rate of change. This one is we got to plug in 9, which is going to give us, if I plug in 9, I get 81 minus 81, so I get 8. So what we're doing, again, I'll just show you, h of 9 minus h of 3 over 9 minus 3, which if I plug in 9, I get 8. If I plug in 3, I get 3 squared is 9 minus 27 plus 8. That gives me negative 18 plus 8, which is negative 10. And this would be all over 6. So I get 18 over 6, which is 3. Right? So then we want to order these. What's the biggest one? Well, g of x is the biggest. Right? The next one is h of x. No, the next one is f of x, which was the graph, because that's 5. And then the last one is h of x is the smallest, right? So h of x is the smallest, f of x is in the middle, g of x is the biggest. So you'd go to this and you'd say h of x is the smallest, f of x is in the middle, and g of x is the biggest. So they have it written slightly different than me, but h of x is the smallest, f of x is in the middle, g of x is the biggest, and that would be the correct answer for that. Okay, so that's that, and I just want to remind you that we're talking about average rates of change, right? Like the slow, like these average rates of change aren't always the most informational things, because really the rate of change changed a lot differently, right? Like this graph went way down, then way back up, and all we captured was that, you know, between 3 and 9, it went up about 5. So average rates of change are only useful to a point. What would be better is if we knew the average rate of change between every single value, and that would give us a better picture of what was actually going on, right? But today we're just practicing how to find it. All right, so the homework again is on Delta Math. Please reach out with any questions that you have.